is going to help you complete the notes from Unit 10.1 on Intermolecular Attractive Forces. You've already gotten the notes on the first 2 pages of this document from the slideshow, and so what I'm going to do in this video is help you complete this chart. So this chart is a summary of the intermolecular attractive forces and how they affect boiling point temperatures. We have 3 intermolecular attractive force types. We have London dispersion force, we have dipole attractions, and we have hydrogen bonding. London dispersion forces are formed between nonpolar molecules, and they are weak intermolecular attraction forces. They are weak. This results in those molecules having low boiling point temperatures, right? And this is because it will take very little energy to separate those molecules from the liquid state where they're close to the gas state where they're far apart. It takes very little energy because they are weakly attracting one another. So it takes very little energy to boil the liquid molecules into the gas phase. Okay, so a couple examples that we're going to use here. The first one that I'm going to show you is methane, which has a structural formula that looks like this, CH4. And methane has a boiling point of negative 161 degrees Celsius. Another example I'm going to show you for London dispersion forces is a molecule called ethane, which is very similar to methane. Instead of 1 carbon, this molecule has 2 carbons, and then each carbon has 3 hydrogens attached around it. So this has the chemical formula C2H6, and ethane has a boiling point of negative 89 degrees Celsius. So these are both pretty low boiling points. It does not take very much energy to turn them from a liquid into a gas. But what is noticeable is that ethane has a significantly higher boiling point than methane. This implies that larger nonpolar molecules, because they have more electrons and therefore a greater chance of a charge separation, that means that larger nonpolar molecules have the chance to get still weak intermolecular forces, but stronger weak intermolecular forces. So London dispersion forces are still at play here, but the larger the nonpolar molecule is, the higher the boiling point will be, because you can get that temporary charge separation happening to a greater magnitude, simply because there's more electrons. All right, let's take a look at dipole attractions. These will be the intermolecular attractive forces between polar molecules. They are considered, we'll call them strong by comparing them relatively. Polar molecules will have a stronger intermolecular attractive force than London dispersion forces and nonpolar molecules. This means that the boiling point temperatures will be higher by comparison. And here what I'm going to do to show you for an example is something called chloromethane. Okay, so this is like taking a methane molecule, taking off one of those hydrogens and replacing it with a chlorine. So if I were to draw that molecule, we might have something that looks like this: 3 hydrogens, and then the 4th spot is being taken up by a chlorine. So now what we have is, this is a polar molecule. It's no longer nonpolar with the addition of the chlorine, it's the Cl. And because of that, we're going to have dipole attractions, a stronger intermolecular attractive force. And the boiling point temperature that we see for chloromethane ends up being negative 24 degrees Celsius. So we can see that the progression of the boiling points is getting higher and higher, meaning it's taking more energy to turn these substances from a liquid into a gas, and that is all due to the increasing strength of intermolecular attractive forces. All right, let's take a look at the hydrogen bonding. This is a kind of intermolecular attractive force formed between very polar molecules. And the strength here, we can say comparatively, is very strong and results in very high boiling point, especially by comparison, right? So if we now take, and we've already seen that hydrogen bonding, you have to have a hydrogen bonded to either a fluorine, oxygen, or nitrogen. So we're going to show an example here showing the progression of these boiling points. We're going to start with our basic methane molecule, this CH4. We're going to take off one of these hydrogens and put an oxygen in its place, and then we'll attach this hydrogen to the other side of the oxygen. So if this is a molecule called methanol, and the difference here is that we've got the carbon with the 3 hydrogens, but then instead of the chlorine, or instead of a hydrogen, we're going to have an oxygen, and attached to that oxygen, we are going to have a hydrogen. Okay. So what we have here is when you have a hydrogen directly bonded to an oxygen, right, that makes this molecule very polar because of the big electronegativity difference. And so because this is a polar molecule, we see, this is not a double bond, this is a single bond, by the way. We see the boiling point temperature for this substance to be 80 degrees Celsius. So significantly higher when we have hydrogen bonding between molecules, the boiling point is going to be significantly higher than it is between polar molecules. So this is a good indicator, good measurable indicator of increasing strength of intermolecular forces and their impact on boiling points. All right, this concludes our lesson on intermolecular attractive forces and their effect on boiling point temperatures. We'll see you back in the classroom.